All right, make sense? All right. So now with this type of basis, we can discuss the first equation we now are able to solve using finite element, the Poisson's equation. And Poisson's equation with zero Dirichlet boundary condition, right? Because we will talk about non-zero boundary condition later on. For non-zero boundary condition, you have to represent the solution not just as an element in the linear space. You have to say the function is a fixed function plus, I mean, the solution is a fixed function plus a member of the linear space, because if you fix a boundary condition to be non-zero, okay, and say all the functions that satisfy the boundary condition is actually not a linear space, because if you multiply the function by 2, your boundary condition is multiplied by 2, so you are no longer a linear space, right? So you need to do something different. So let's start with a zero Dirichlet boundary condition. Okay, so the Poisson's equation we will be solving is oh, and by the way, let's solve it in one dimension, so we actually are solving an ODE. Okay, so d square of u dx squared plus f is equal to 0. All right. And the first thing we'll do is that we want to restrict the u into our x. We don't want to look for solution anywhere. We want to look for solution within our space, right? And as we refine the grids having more elements, we know that our solution space is richer, right? It can contain more functions, and therefore we expect our solution to be more accurate. So let's say our solution is x, which is and by the way, we are going to represent our solution as this ai times hi. So this is our basis, expansion into the basis. Okay, and then we are not going to be forcing the equation to be exactly satisfied, right? We are saying, okay, I'm going to get a residual equal to r, but I want my r projected into the space of x to be 0, right? Or in another sense, r is the element that minimizes r minus 0 in a product with r minus 0. Does it make sense, right? So r may not be in the space x, right? But 0 is going to be the closest point, or I should say arg min of f with r minus f is equal to 0, right? That's a better way, that's a more rigorous way to say it. So for if I choose f within the space x to minimize the distance between r and f, my f that comes out would be 0. Questions about this? Yes?
What are you saying when you're saying that we're making our solution in x?
That's basically saying that I want my solution u to be a linear combination of ai times hi, right? Or I want a solution, I want a piecewise continuous and linear solution.
Okay, you're not saying that the true solution...
I'm not saying the true solution is in x. We're only looking for the solution. We're looking for an approximate solution in x.
Okay.
Yeah, just like we are approximating a function with a piecewise linear continuous function. We are now approximating our true solution with a piecewise continuous, piecewise linear and continuous solution. Okay, and the approximation has to be such that the residual projected into the space x is going to be 0. Right, and this, as we just analyzed, is equivalent of saying for any df, okay, df inner product with r minus 0 has to be 0. Right? Okay, you can go through the same math and show that's exactly what we did before. Or let's plug in the definition of R. This is saying for any df inner product with d squared u dx squared plus f is equal to 0. All right. Okay, so now let's plug in this u. Let's plug in this u. We get a df summation, it goes from 1 to n, ai times the d square hi dx square plus f has to be equal to 0, and we use the property we call the bilinearity of the inner product. We get summation ai df d square hi dx square. So this is one term. Another term is df, f has to be 0. Right? So this is basically expanding the inner product as if it is just a product. It always works because of the properties of the inner product. Can somebody see that we get a ax equal to b? Right? We get an ax equal to b. So, but just in this case, the a and oh, sorry, not yet. We also have to say the df. Right now is still any function, right? And again, because df can be represented as a linear combination of the bases, so we only have to enforce this equality for a finite number of df's. That's enough to enforce this for any df. So that is a summation of this ai. Instead of df, I have hj. So this is for any df. Now this is for any j, goes from 1 to n. Hj d square hi dx square plus hj f has to be equal to 0. Now it's truly ax equal to b. So the ax equal to b would be x, again, is the ai's, a1 to an. The b's are h1f to hnf, right? And my aij would be this actually my aji is hj d square hi dx square. All right. So the procedure for using finite element to solve the Poisson's equation would be, I get my right hand side, I would take the inner product, which is simply an integral of my right hand side with each of the basis functions, with each of these functions that goes up and down, right? And by the way, in this case, my number of basis functions is 1 less than the number of elements because I have boundary conditions on both sides. So I take these inner products, so all of the basis functions are head functions. So I take the inner product, I take the integral of the head functions times the f, okay? I populate into the vector b, and also I compute the inner product of the head functions themselves with the second derivatives of the head functions, which are actually delta functions, right? The head functions, the second order derivatives are basically 0 everywhere except for the kinks, right? So I get basically 3 delta functions on this second order derivative, and these are going to be multiplied with a different head function and integrated. So these are going to be my matrix. and then I do Ax equal to b. I solve the matrix system to get my x. Again, once I get my x, I know the linear combination coefficients, which for these head functions are actually the values of the solutions at the grid points. So then I have my approximate solution. All right, so this is how we solve equations in general with finite elements. And this is a particular example. There are still several deficiencies in what we described. Boundary condition is one thing. We are only able to solve zero Dirichlet boundary condition. Another thing is there is a more mathematically rigorous way to deal with cases where we get delta functions in the derivatives, and we also discussed that. And yet another thing is, how do we know how accurate our solution is, right? So that's another thing we will discuss.